Hey everyone, if you're getting ready for your Class 10 physics exam, there's one topic you absolutely have to master, and that's Ohm's law and resistance. In this explainer, brought to you by A1 Institute, we're going to break it all down and get you 100% exam ready. So, have you ever stopped to wonder why this happens? You know, a copper wire is basically a super highway for electricity, but the plastic wrapped around it is like a total dead end. What's the secret? What's really going on there? Well, the answer is just one single powerful idea: resistance. It's the property that decides whether electricity gets a green light or a big red stop sign. And by the end of the session, you're going to understand it completely. Okay, here's our game plan. We'll kick things off with the main rule. That's Ohm's law. Then we'll dig into what resistance actually is, see what factors can change it, and then the most important part, we'll solve some real exam problems. Let's get right into it.
All right, let's start with the foundation, the rule that connects everything: voltage, current, and resistance. This is the famous Ohm's law.
So here's the official definition. In simple terms, it just means that if you increase the electrical push, which is the voltage, you'll get more electrical flow, which is the current. They go up together. But, and this is a huge but for your exams, notice that last part, provided its temperature remains the same. That's a key condition you gotta remember.
And here's the proof you can actually see. If you plot voltage versus current on a graph for a material that follows Ohm's law, you get a perfect straight line. And the slope of that line, well, that constant slope is the resistance of the material. It's a beautiful, simple relationship. And this all boils down to the one formula you need to burn into your memory: V equals I times R. Voltage equals current times resistance. Trust me, this little equation is your best friend for solving a ton of physics problems. So we've got the rule down, we've got the formula, but what is this resistance thing, really? What's happening on the inside of that wire? The easiest way to think about it is like electrical friction. Imagine electrons trying to sprint through a crowded hallway. They're going to be constantly bumping into atoms, getting slowed down, and having to change direction. That chaos, that opposition to their flow, that's resistance. And based on how much friction they have, we can sort materials into three basic groups. Good conductors, like your copper wires, have super low resistance. They're like an empty hallway. Insulators, like plastic or rubber, have crazy high resistance. It's a total wall. And then there are resistors, materials made to have just the right amount of resistance for specific jobs at a circuit. Okay, so every material has some resistance. But is that number set in stone? What if you take a really long wire versus a short one? Or a thick one versus a thin one? Does that change anything? Oh yeah, it absolutely does. Let's look at the factors that change a wire's resistance. There are four main things that decide a conductor's resistance: how long it is, how thick it is, what it's made of, and its temperature. Let's really dig into how its physical shape, length, and area makes a difference. First up, length. Think back to that crowded hallway. If the hallway is really long, you have a lot more chances to bump into people, right? It's the exact same for electrons. A longer wire means more material to navigate, more collisions, and therefore higher resistance. It's that simple. Next up, the area, or its thickness. Let's switch to a traffic analogy. A huge 8-lane highway can handle tons of cars smoothly, but a narrow little country lane? Instant traffic jam. It's the same for electricity. A thicker wire is like that highway. It gives the electrons more paths to travel, which means lower resistance. And finally, there's the material itself. This intrinsic property is called resistivity, and we use the Greek letter rho to represent it. It's what makes copper naturally less resistive than iron. This allows us to tie everything together in one master formula. Resistance equals resistivity times length, all divided by area. R equals rho L over A. Okay, the theory is cool, but let's be real. You're here to pass your exam, so it's time to put this knowledge into practice. We're going to solve some classic problems you might see on your test, right from your textbook.
All right, here we go. Problem number 1, based on example 11.3 from your book. We've got a voltage of 220 volts and a resistance of 1200 ohms. The question is, how much current is flowing? So, how do we attack this?
Let's use a simple, foolproof method. First, write down what you're given. Voltage is 220, resistance is 1200. Easy. Next, what's the formula? We know V equals IR, so we just need to rearrange it to solve for I. That gives us I equals V divided by R. And finally, the solution step. Just plug in the numbers. I equals 220 divided by 1200.
Do the math and you get 0.18 amperes. And that's it. By following these simple steps, you can tackle these problems with confidence every single time.
Okay, you ready to level up? Let's try a trickier one, based on example 11.6. This really tests if you understand the factors. We have a wire with 4 ohms of resistance. Then we chop its length in half and double its thickness. What's the new resistance?
Okay, let's break this puzzle down. First, what are we given? The initial resistance, R1, is 4 ohms. The new length, L2, is half the original, and the new area, A2, is twice the original. Our formula is the big one, R equals rho L over A. Now for the solution. We're looking for R2. We plug in our new values. We have L1 over 2 on the top and 2 times A1 on the bottom. Now just look at the numbers. We have a 1/2 on top and a 2 on the bottom. What's 1/2 divided by 2? It's 1/4. So our new resistance is just 1/4 of our original resistance. And since the original resistance was 4 ohms, a quarter of that is 1 ohm. Look at that. By making the wire shorter and fatter, we slashed its resistance down to just 1 ohm. This is a perfect example of how those factors work in the real world.
And just like that, you've used the core concepts we talked about to solve a pretty tricky exam-style question. You now have the fundamental tools to master this entire topic. So, what's next for you?
Well, if this explainer helped you out, the best way you can help us is to hit that like button, share it with a classmate, and leave a comment. And definitely subscribe to the A1 Institute YouTube channel for more lessons like this. And of course, if you're looking for detailed notes, admissions help, or expert guidance, please contact A1 Institute. All the details are in the description below. We'll leave you with one final thought to chew on. Today, we've totally mastered how a single resistor behaves. But what happens when you start linking 2, 3, or even more of them together in a circuit? Now that's an interesting question, and it's exactly what we'll cover next time. Thanks for joining us.